the propagation of the light. And the second one is the particle property, so wave and particle, which are the dual personalities of the light, or the two personalities of light here. And for the particle property, which is shown by some processes like emission or absorption. Like when I just mentioned with you about the photo effect, for example, if you shine the light to some metallic surface, and then somehow we can observe, depending on the wavelength we inject, and also depending on the kind of the metallic we use as well, the metal we use as well, we will observe some electron current, right? So this kind of effect, in fact, they can also explain by, people can also explain this photo effect by two considerations. Both light is a wave, but it seems to be easier when we consider light as the bunch of the photons. So it is a particle properties. So for the emission process, or even for the absorption one, in which light shows that it is like the particles. So it is the one thing. Or like some applications we are using nowadays, like the lasers, for example, the light amplification by stimulated emission radiation. So this one, because you guys more or less study in ICT mainly. So here I mentioned some example, not related really close to your domain, but you see here the laser one, which in which it can be produced like in the 1960s, thanks to the particle properties of the light, in fact, in which you have the SE stands for stimulated emission. Yes. So, and in order to have this kind of stimulated emission, we need to put the absorption first. So you need to inject some energy for the atoms so that it will gain this kind of energy. So it absorbs. This is the absorption process, and it will jump to the excited state, and then it will move to the another lower state, and then it can make the stimulated emission one, and then it generates the laser light amplification by stimulated emission radiation. It is the what we have for the laser. So using the light is very nice, right? Showing you here in this figure is an electric cook, right? I mean here we use this. We use the electric heating pot here, and you see the color. At first, it's not red like this one. When you provide the electricity to that, it is hotter. Yes, we know that. However, at first, the red color does not appear, even you feel some heat. So at first, this will emit first the IR radiation. So IR means infrared. So infrared, the wavelength is longer than the red here. So that's what we call the infrared. And longer wavelength, that means smaller energy. So at first, it will emit the primarily infrared radiation. And then when the temperature is high enough, it will be also becomes red, it also becomes red like this one. So it emits a discernible amount of visible light, is how we can observe here. And for the light, one important quantity is the speed of light. Light is an electromagnetic wave. Yes, we agree with the development of the knowledge, we know that. And any kind of wave must travel or propagate at some velocity. And for the light, the speed of light in vacuum, which you know so far very well, this value, right? See, approximately to 3 × 10⁸ meter per second here. And at USDH, in fact, we have some setup in order to measure the speed of light as well. And for sure, we don't carry the measurement in vacuum. We don't have the condition of the vacuum here. for the lab work, I mean, of this type of measurement, but you can do that in air, and then the values is very close to this value. And we also measure when the light travels in some materials, like in the water or some glass as well. So for the TB, for the practical work, it is fine for the COVID-19, we say. Now it becomes better. You can come back to the university, come to the lab, and then for the practical work of the fundamental physics too, you will have a chance to measure the velocity of light, the USDH. Some quantities related to the light are light is an electromagnetic wave, we agree. We will deal with the wavefront and rays as well, so wavefront. Okay, so wavefront, what it is. Wavefront here, this concept, wavefront is the locus of all adjacent points at which the phase of vibration of a physical quantity associated with the wave is the same. So it is a collection of all the adjacent points at which the phase of the vibration of the physical quantities should be the same. So here, for example, showing you here is an example of the sound wave here. So the red dot here shows us the sound source here. So we got a point sound source, and then it can produce the spherical sound waves here. So in order to be able to hear something, in fact, we have the compression and rarefaction, right, of air as well. So we got that so that we can have the traveling of the sound. And here you have the spherical sound wave here. So on the point, on the adjacent point, in this curve, for example, here, all of them are called the wavefront. Yes, the wavefront here. You got this wavefront, and this wavefront, and this wavefront, etc. Also, because we got the expanding wavefront, the expansion of the wavefront surrounding this point sound source. So here's the example of the mechanical wave. And similar to the case of the light, we also have that as well. So we also have the terms of the rays here. So wavefront, which is the locus of all adjacent point here, at which the phase of vibration of physical quantities should be the same. Pay attention to that. So for example, we have here the source, which produce here the wavefront in spherical here. On wavefront here, we denote spherical. Yes, from the center of the sphere. So you got the wavefront. Okay. And the definition for the rays, if we consider light is the particle, or if we use the particle theory of light, so it's simple to imagine, right? In this case, rays are the paths of the particles. Very obvious, no doubt to that. And if we believe that light is a wave, and indeed it also has the dual properties like this one, right? So for the wave viewpoint, in that case, rays is not the actual rays anymore, right? It should be an imaginary line, like what you use for the when you describe the electric field, for example, you want to show the electric field lines, and then sometimes you will use some imaginary lines to describe that. So for the wave viewpoint, rays are the imaginary lines along the direction of travel of the wave. So here you got this source, and it produces the wave, and the wave expands in this direction, like this one. So rays are here. So it will shows the direction the wave travels. So you got that. The blue curve shows the wavefronts, and the violet lines show the rays. If we move very, very far away from the source, like we go very far away. So in that case, the spherical wavefront, when we get further, it should become something like planar, like this one, right? Yes. So here you got, in this case, we have the wavefront, in this case, are planar. Or sometimes we have the so-called plane wave as well. For the source, for the light source we use. And in that case, the rays will become parallel to each other as well, because the rays here perpendicular to the wavefront. Always the rays are perpendicular to the wavefront. We have this at this point. You draw the tangent line, and then you draw the line which is perpendicular to the tangent. Okay. And then when you draw that kind of tangent line at this point, for example, so the rays must be perpendicular to this tangent line. If we consider the spherical wavefront, and when it becomes planar like this one, the rays should be perpendicular to that wavefront as well. So it's what we have the concepts of wavefront and rays. Now we will move to the second section of this chapter. We will deal with the propagation of light. So to begin, we will study the very popular, very basic one. You already know very well that, which are the reflection and refraction. So reflection and refraction. So now we will enjoy this figure. We look here in this figure, there are a woman, right? Two men drinking coffee inside the coffee shop here, Alice Coffee Shop. And there is a glass window here, okay? And due to some wind, the head of this woman flies like this one. So when we observe some object in surrounding Earth, in fact, it is the light help us to observe, right? The light when goes from the object to our eyes, and then the interaction between the light and the object and some optical devices will produce some kind of image, and what we observe is that kind of image. Is how you observe the surrounding world. Here we go. In this case, when this woman look at her head, yeah, so in fact, her head is here, and she can observe her head is that this head, the incident, you have termed the incident. As incident rays come from the head to the mirror. Here we got the mirror one. And then the incident rays will be reflected. Yes, it will be reflected, because if this incident ray or incident wave travels in air like this, and then it faces an obstacle, which is the mirror. So at the boundary between the air and the mirror, or we say the interface between the air and the mirror, the wave will be reflected. Yes, and that's why we see the reflected image of the head here. It is one process or one optical phenomenon. Now, for these two guys, sorry, for two men who are sitting here, and then the incident wave from the head, yes, with the support of the light for sure, propagates to the mirror. So air and then mirror. So normally the mirror is made here with a glass, for example. Sometimes they will cover with the silver part, so that you will have the no transmitted, right? And in this case, we have only glass, so the light can be transmitted as well through the mirror. However, due to the difference of these two media, one is air, one is glass, so the light cannot go straight like in air anymore, but it will be bent a little bit depending on the relationship between the two media. So here we got the refracted wave, yes. And then this man sees reflected image of the head. Yet it is so it is what we look in this situation for the reflection process or reflection phenomenon and the refraction phenomenon as well. So the light bounces and reflected. The light transmitted here, the light transmit and refracted here. Okay, so it's what we observe in this figure. So the waves in the outside air and glass represented by rays here. We use the rays here. In this case, and also here, this rays, the incident rays coming from outside in air in the material or the medium A. And when it meets the interface or the surface between material A or medium A and material B, or to say like medium or environment B. So there is something happen, right? First phenomenon is the reflection here. So we observe the reflected rays. So incident rays, because we consider that the rays come from the source, which is quite far away. So you got parallel incident rays. And we got the reflected rays here. Also, they are parallel to each other because you remember or you know so far the law of reflection, yes. And if the surface is very smooth, then we will have the reflected rays will be parallel to each other as well, because each angle here will be equal to each other, right? And what happens inside the material B is that also we got the refracted rays. However, these rays now go in this direction. It's not the same direction as the incident rays anymore, but they bend. You see, they bend. We use the word bend. Okay, you see bend here. And furthermore, people can abuse this type of phenomenon in order to create some bending optical structure as well. So here we got that. So the incident ray here coming to this interface. And then in order to draw the reflected ray as well as the refracted rays precisely, we need some mathematic tool, right? Yes, we need some law to show the relationship between the reflected rays and the refracted rays. In order to do that, first, we will draw a line which is perpendicular to the surface or the interface. So the name of that is the normal. Normal. So in the figure showing you here is a dash, the black dash dot line is perpendicular to the surface, or we say the interface between two. And if you have only one material, and then you got only the surface here, the interface here, so the incident ray will come to this surface at this point, and then you will draw a line passing through this point and perpendicular to the surface, which is the normal. So also I type in the chat box as well. So please also follow the chat box so that because we have the online class, so sometimes I say like this one, but I'm scared that maybe we will miss some information. So I also write it down in the chat box as well. So first we draw the normal. Okay, cool, right? And then the relationship between these rays will be described by the angle. So here you got the material A and you got material B as well. So they denote the angle here in the material A, theta A. So the theta A, and also please pay attention to the arrow they use here. The arrow shows from the normal to the incident ray. So theta A is called, theta A is called angle of incidence, or sometimes I call incident angle. Incident. Okay. And it is formed from the normal to the incident ray. And also I want to remind that you can use other notation for theta A. If you like, you can use theta I, like I stands for incident, as it's okay. Or you can use theta 1 as you like, okay? Never mind about the notation. Just the relationship between them is important. The notation is not so necessary for us to be like, we need to use this kind of notation. No, okay? So theta A here in this figure is the angle of incidence. And for sure, the angle of reflection, theta R here, theta R, angle of reflection. Or we can say the reflected. Yeah, so we've got reflected ray here and the angle created from the normal to the reflected ray. This is what happened to the so-called reflection. And for the refraction, we look at the material B because the refraction happens in another material. So the incident rays like this one and the refracted rays will be bent. So not the same direction, but now it will be bent. So closer to the normal or get away from the normal. It is two situations depending on the relationship between the two materials we will discuss in detail right after. So we got the refracted rays, and the angle between the normal and the refracted rays is called the angle of refraction. So you got theta B. So angle of refraction. So we have two cases for the reflection. If you have a very smooth surface, so this kind of reflection is called specular. So parallel incident rays and then parallel reflection rays as well, right? As we see here, the reflected rays are parallel as well. However, what is more in our real life is that the surface is not totally smooth, but it should be rough. And how we can observe the object surrounding us is the light from the source coming to the surface of the object and reflected to our eyes, and then we can capture that kind of object surrounding us. And here, if we have rough surface like this one, so incident ray in this direction and then reflected rays in this way. Here also we got both three parallel incident rays. However, the first reflected rays in this way, the second reflected ray is in another way, and the third reflected rays here is also in another direction. So the reflected rays are very difficult to be parallel to each other, right? So it is a so-called diffuse reflection. And for our case, we will more or less focus on the specular reflection only for the calculation, for the ease of the calculation. We will consider this case, except some kind of exceptional, we will deal with the diffuse reflection in the textbook during the course, and also in the exam, we will deal with the specular reflection. But keep in mind, what happened more popular surrounding us is the diffuse reflection. And I just mentioned the refracted rays, the direction of it will be dependent will be dependent on the relationship between the two materials. So which kind of this kind of relationship, right? So showing here is the formula for the parameter or the quantity which describe the optical behavior of the material. It is the so-called index of refraction. So if you look at this figure and we see theta A like this one, and theta B smaller than theta A, and if you also a good student in physics, you will at once, even if we don't know exactly what materials are for material A or in material B, but we can easily understand that the refractive index of the material B is larger than the refractive index of the material A, right? So this angle is smaller. So, and it is also provided by a law we will also study in the next part right now. And here, the relationship of the index of refraction or the refractive index between these two materials will define also the direction of the refracted ray. Okay, so N equal to C divided by V, because the so-called index of refraction will shows how the light changed its velocity in that material. So in vacuum, it is the largest velocity of light, 3 times 10 to the power 8 meters per second. In other materials, for sure, the light will be slowed down. And how it slowed down is depending on the index of refraction, or we say the refractive index, which is the ratio of the speed of light in vacuum to the speed of light V in the material we consider. Okay, so it is the important optical quantities. So sometimes we, sorry, I come back to here a little bit. Here. When we say that this is optical denser or less dense compared with these two kind of materials, it's related to the index of refraction. So keep in mind N equal to C divided by V. So like we know so far, air and approximately to 1, water 1.33, right? And also some glass around 1.5, for example, silicon 3.46, 3.48, also depending on the values of the wavelength, which we will discuss in the section of dispersion as well. However, it shows how the light slows down in that kind of materials. It's one thing. Now we will have a look at the laws of reflection and refraction. So we know that yes, the light changes the direction when it faces some kind of interface. When it meets some interfaces, it will change the direction. In order to draw it precisely, the direction of the reflected ray and the refracted rays, we will need some mathematic tool. It is a concept of physics phenomena plus mathematic formulas, always like that. So here we go. We will have a look again what you also know so far about the laws of reflection and refraction. So here, incident ray and reflected ray. So the reflected rays, it is named reflected rays because it also lies in the same material as the incident ray. Yes, you see here. Only different side along the normal. So the normal here split the two part, incident ray in this part, and the reflected rays in another side. You see here. And the relationship between the two angles, the angle of incidence and the angle of reflection, should be equal to each other, is what you know, right? And for the refracted rays here, it will depend on the relationship between the refractive index of material A and refractive index of material B. And then we also show you right now as well, again, what you also know so far. Here's a normal, yes. And they are the angles, theta A. And keep in mind, theta A formed from the normal to the incident ray. Theta R, the angle of reflection is created from the normal to the reflected ray. So we got theta A and theta B are measured from the normal. So pay attention, the normal here, and then theta B here. And we see this incident reflected and refracted rays and the normal as well. These 4 lines, they all lie in the same plane. Yes, same plane. And the reflected rays lies in the same materials with the incident ray. The refracted rays for sure lie in the different material with the incident ray, different materials. And always they will be in different side from the normal compared to the incident ray. So pay attention. They're not in the same side. When you draw, don't make the mistake. A lot of students also make the mistake like here we have the incident and then the refracted in this direction. So pay attention, refract here. Okay. From the normal, it will separate the incident rays and the refracted rays. 2 sides different. Okay. And for the law of reflection, yes, which you know so far, we got theta R equals theta A. So the law of reflection. And when you write the formula in physics, also in math as well, pay attention. What the induced property or the induced quantity should be on the right-hand side of the expression, and on the left-hand side of the equations, and the right-hand side will show the what we already know. I mean the first quantity should be on the right, and then the induced quantity should be on the left. So theta A here, which we should know when you inject the light like this one. So you write it on the right-hand side. So theta R is something depending on that. So that's why you write on the left-hand side. For the mathematical point of view, if you write theta A equal theta R, okay, it's good. However, for the physical point of view, you should write what induced on the left, what you know on the right here. Yes, it is the spirit I want to share with you. Even it's quite a small point, but pay attention to that. Now we will have a look in detail for the refraction. Yes. So in this case, if we consider the situation in which the refractive index of the material B, or we say the index of refraction of material B, is larger than the refractive index of material A, and B larger than NA. So the incident rays like this one, yes, for sure we got the reflected rays in this direction. And then for the refracted one, now we focus on the refracted ray here. So in this case, you see theta B is smaller than theta A, right? So the angles of incidence, angles of refraction, the relationship between them, and also the refractive index, they have the relationship. Here we go. If we consider the case in which index of refraction for material B is smaller than the index of refraction for material A, so you see theta B now is larger than theta A. Okay, so that's why we call N the index of refraction in this manner. So it also affects to the direction of the refracted ray. That's why. Yes, the content of the law of reflection, we got here the angle of reflection, theta R is equal to the angle of incidence, theta A, for all wavelengths and for any pair of materials. Yes, you have any arbitrary pairs of materials, and at the interface, the reflection happens, and always the angle of incidence and the angle of reflection will have the same value. Okay, and for the refraction, we got the relationship between the angle of reflected and angle of incidence in this manner. You got sine theta A over sine theta B equals NB divided by NA. So that's we got the so-called like the refractive index, or we say index of refraction. and angle of, say for short, and the angle. So higher refractive index in these materials comes with a smaller angle here. And you can have NA multiplied by sine theta A equals NB multiplied by sine theta B. So it is the law of refraction. And the name of this law is Snell's law. So you guys already abused or applied this law a lot. However, I don't know if you know the name of the law or not, right? So pay attention after this course. I do hope that you all know the names of the physical laws as well. It's also like to respect the scientists or the guys who discover that content. So here's the Snell's law, a Dutch scientist. Snell is that a Dutch person here. So we got the ratio of the size of the angle theta A and theta B, where both angles, pay attention, are measured from the normal to the surface, but from this type normal to the surface, is equal to the inverse ratio of the two indices of refraction. So here, you've got the product equal to each other, right? Yes. And the sine of these two angles are equal to the inverse ratio of the two indices of refraction. So pay attention on that, and it is a Snell's law. Okay. Oh, so slow. Now we will discuss some phenomena happening in our daily life. Yes. So if we dip a ruler inside the water like this one, so this part is in air and another part is inside the water. And if you look at the ruler, at first, if it is in air, we see that it's straight. Yes, a straight ruler. But if we immerse it inside the water like this one, and we feel that the ruler is bent, right? So in order to explain this, it's also very easy. Yes. Here is the ruler. And pay attention when you observe, when we observe some object, in fact, we will observe the image of this object. So here, this part is in air and this part is in the water. And if we look at the end point here, the end of the ruler, when we observe this, so the light from the end point will propagate to our eyes, you see here. So this go in here, and at this point, if you want to draw exactly, you need to draw the normal. So the angle here should be smaller compared with the angle in the air, because here is in the air, right? So following Snell's law, we see that this will be bent further to the normal. And also this refracted rays as well. And these two refracted rays meet at this point. So this point is the image of the end point of the ruler. So now the ruler at first is like this. However, our eyes think that it is the ruler now. That's why the ruler seems to be bent. So pay attention when you draw the image, you should show the direction of the light like this one come to our eyes. Also, you can choose these two arbitrary lines or one arbitrary line only, and then you can draw also the another incident rays which propagates perpendicular to the surface. You choose that, it will be so easier, right? So here is what happened, yes, due to the refraction, and then we observe that. Also, we can explain why the setting sun appears flattened vertically as well. So we see the flattened here. So it due to the difference of refractive index of the atmosphere as well. That is a different location. So lower, that means denser. Farther, that means less optical. So behavior, or we have smaller refractive index as well. So that's why due to the refraction, and we will have observed the suns with this type shape, while straight, right? Showing you in this table are the refractive index or the index of refraction of different substances. So you see the some solids, some glass, some liquids, solid like ice, diamond, rock salt, or the glasses we have here in this list. And also we have the measurement, the experiment as well to verify the velocity, the velocity of light, yes, and also the values of the refractive index of the glass as well as USDH. I do hope that you have a chance to do this work as well. Okay. And one property is that the path of the refracted rays and reflected ray and wave, or ray and ray, okay, is reversible. That means if you inject the light from here, and then you got the reflected rays like this one, and the refracted rays like this one, and if you change the position of the light source, you will have the same direction as well. Okay. And if NA is larger than NB, and then NA is larger than NB, so in that case, the ray is bent away from the normal. So you see this angle is larger compared with this one. So the angle of refraction is larger than the angle of incidence. If the refractive index of the material B is smaller than the refractive index of material A. Yes, smaller refractive index, larger angle. Just keep in mind that. And if NA is smaller than NB, and then this angle will be smaller, and then we say that the ray is bent toward the normal. Yes, so this is the properties deduced from the Snell's law. And the intensities of the reflected and refracted rays depend on some parameters. First, the angle of incidence. Yes, we totally agree, right? The two indexes of refraction. Yes, we do agree as well, following the Snell's law. And also the polarization. And for the polarization, we will study in detail for the part of the polarization. And in that, you will see how it depends. Yes, it related to the Maxwell equation invented by James Clerk Maxwell, but in fact, the intensity will be proportional to the electric field, and the electric field, the direction of the electric field will decide the polarization of the light. So that's what we say here, the intensity of these two reflected ray and refracted rays will depend on the polarization. We will discuss that in the session 1.4 or 1.5. I don't remember very well, but we will do that right after. The index of refraction we just mentioned before, N, right, equal to C divided by V. So it is the ratio of the speed of light in vacuum to the speed of light in the material, which is the index of refraction. And when the light travels from one material to another one, the velocity in different materials will be different as well. And the refractive index also affects to that kind of velocity. And when we consider light as a wave, so a very popular an intrinsic property of that wave is the wavelength. So you have the term of wavelength, and the wavelengths applied in different materials will be different as well, following the expression that the wavelength of light in the material lambda here equals lambda 0 divided by n. So you see the decrease of the light from when it travels in vacuum with the wavelength lambda 0 to lambda. Here is the wavelength in materials in which n equals c over v, the index of refraction, or we say the refractive index. And we got the term of the wavelength. So I also want to revise with you about the concept of wavelength. So who remembers what is wavelength? So what is wavelength of a wave? If you remember, you can unmute your mic and then speak out loud. The concept of wavelength, what is this?
Teacher, is it the distance of two closest photon?
Two
Closest photon.
Two closest. What? I didn't catch it. I can't.
Photon. The
Photon?
photon.
Photon?
Yeah.
You mean the photon here?
Yeah. That's what I mean.
Yeah. The distance between the two closest photon. It is one definition from one student who, anyone who has another definition for wavelength. It is also a very important concept. That's why I want to spend some time discussing with you about that wavelength. Here we go. Wavelength. The distance between the two photons. In fact, I never use this kind of definition. Indeed.
It's the distance between 2 points, two nearest points with the same phase.
Okay. Yes, we also have another definition from one student. He mentioned that the wavelength is the distance between the two nearest points. So first is the distance. Yet all of you define the wavelength, which is the distance between two nearest points. Which have the same phase, right? You mentioned the same phase. I also
yes.
tried to, yeah, okay. So yes, it is what we normally we use this kind of definition in mechanics when we draw the waves. For example, normally you will draw the water wave, okay, and then we will choose. Yes, and also another student delivered the opinion that the shortest distance between two highest points of the wave. When we mentioned the two highest points of the wave, in fact, they are also the 2 points has the same phase, but the special thing here is that they have also the maximum displacement. So that is they are at the amplitude of the displacement. Yes, for Huang, he mentioned here for that. So it's also similar to the case, the distance between the two nearest points, which has the same phase. Yes, when we deal with that concept is fine as well. On another definition I want to mention with you, maybe you already touched, but you may ignore that. Wavelength also is a distance. I agree. Yes, the main thing is that is the distance. The distance that the wave can travel in one cycle. Yes, cool. I see also Lê Nhật Minh mentioned as well here the distance the wave travels in one cycle. Yes, exactly. So in that case, the wavelength is defined by a wavelength in the notation, which is lambda. So thank you for your contribution during the course. It's very cool. Good. If we have enough time, sometimes I have some examples, and if we have enough time to deliver the idea to solve the examples, you can gain some bonus point also, like 1 point or 2 points, depending on the examples here. So wavelength, in that case, like Lê Nhật Minh just mentioned, and also I type in the chat box, the distance the wave travels in one cycle. So wavelength will be equal to the velocity of the wave, which we denote by v in general. Okay, in vacuum it is c, never mind for the light, but in general it will be v multiplied by the period or the cycle. The cycle, which we normally denote with T. You agree, right? Yes, for the definition for the wavelengths. So the frequency now, if we write in terms of frequency, the wavelength will be equal to the velocity divided by the frequency. F. Okay, because the period of the cycle means the cycle T, we denote T here, means the time, the duration that the particles finishes one oscillation. So the period is defined by that, and the frequency is the number of oscillations in 1 unit time or in 1 second. So that's what we got here, the relationship, the frequency. So sometimes I will write in different order, but we got that kind of thing. So we got wavelength equal to velocity multiplied by period or cycle T, or equal to velocity divided by frequency. So I also saw one direct message from Phùng Đàm Quân to me in the chat box, like lambda equal to 1/f. So please pay attention. In fact, we got lambda equal to V divided by F. T is equal to 1/f. The relationship between the frequency and the cycle, we got that the inversely proportional, and here we got this relationship. So we have here the wavelength, but the frequency should be constant. So the wavelength changes when the light travels from materials to another material, but the frequency constant. The number of the oscillation over a period will be the same. If you follow this kind of definition for the wavelengths, you will be able to prove why we got the frequency constant as well. Yes, you can explain that. Cool, good. We will have one small example related to the reflection and refraction. So it is a chance for us to practice what we just studied. So like after listening to me a lot, now you can spend like some couples of minutes to do this very, also easy examples, what you already learned, even I think from the high school and secondary school, you can solve this example as well. Here, the only thing changed is that we study everything again in the system, also in English as well here. So in this following figure, material A is water. So they also provide the index of refraction for water is 1.33. And I also want to remark with you, when we study in English, the decimal value should be marked by the point instead of the comma. In Vietnamese, we use here 1,33, but we study in English system, so 1.33. So pay attention on that. And material B is glass with refractive index, or the index of refraction 1.52. There are different types of glass and different values for the refractive index of them as well. Here is one example, like 1.52. However, we can have like also 1.54 and etc. as well. So here's one case. The incident ray makes an angle of 60 degrees with the normal. Here is the normal. Find the directions of the reflected and the refracted rays. So this question, when we talk about the directions, that means we find the angle, because the angle here is created from the normal to the reflected rays and the angle from the normal to the refracted rays. So the questions here, instead of they ask you, what is the angle of reflection and what is the angle of refraction, they will ask you, find the directions of the reflected and refracted rays. Okay, so that you should be able to draw that as well. And find the angle between the reflected and refracted rays. Okay. This morning, when I moved to this example, I also solved as an example as well. But however, to this afternoon, I when give you this kind of chance in order to solve this example. So now it's 14:15, so 2 minutes. You have 2 minutes, and then if anyone who want to tell about your solution, tell us your solution, you can speak out. Okay.
Can I speak out my solution?
I think for sure I have. Let me see. So who are you? Because I couldn't see the
I
participant.
am Nguyễn Hoàng Tùng.
Okay. And your ID, because I need to know. So if you have some, you obtain some midterm bonus point. So Nguyễn Hoàng Tùng.
My ID is BI12 475.
475, right? So BI12 475, and you are the student in which specialty?
I major in ICT.
Okay, cool.
Mỗi thằng kia bận rồi, không thể nào đâu.
And sometimes it's open your mind.
Được chưa? Mẹ công năm ấy đây, được chưa? Sinh viên đấy được.
How can I mute this one?
Vì đổ hũ luôn rồi.
Vũ Anh Tuấn, right? Mute your mic.
Alo cho các hai mà đánh chắc là đánh đồ biến thôi.
Lấy tiền hóa bất ổn mà.
Đồ biến gì?
Lấy tiền hóa bất ổn mà cần gì thế nào?
Đồ biến rừng.
Ê ông bạn ơi, tắt mic đây.
Cái đồ biến rừng với cái lói mạnh ấy muốn ra nó khỏe.
Yo.
Thằng đấy mà đép được nó.
Chúng ta kính qua mà.
Đem mạnh quá.
Rôn đéo.
Vũ Anh Tuấn hình như không nhận ra có bạn nào có số điện thoại gì của bạn Tuấn thì có thể nhắc bạn rồi. Okay. Okay, so Tùng, go ahead for your solution.
So the direction of the reflected ray, is it technically just the theta of B? I mean theta of R, the direction of the reflected ray. So
Okay.
the direction of the reflected ray is so the direction of reflected ray is equal to the angle of the reflected ray, right? Am I correct?
Yes, the direction of the reflected rays, in fact, is the angle of reflection.
So the direction of the reflected ray is equal to 60 degree. And the direction of the refracted ray is approximately 49.27 degree.
Mm-hmm.
And the angle between the reflected and refracted ray is the direction. It is let's see, it's I don't think I got the right answer for this one.
Yeah, for the angle between the reflected and refracted rays, you mean? Yes. How can you solve that? You can tell the idea to solve that as well.
So I plan to so we have a flat plane, which is the degree of 180.
Perfect.
And next we will subtract the other angles. That one which is we will subtract with 60 degree and 60 and 49.27. And the result should be let me see, let me just do the calculation real quick. So it should be approximately 70.7 degree.
Okay, so again, you yes, is your answer, and you also mentioned the way you calculate for the second questions. For the question of the direction of refracted rays, could you please explain how you can solve that? You deliver like 49, as I remember well, 49 degree, right?
49.
Yes.
I use the Snell's law to do this.
Yeah. Okay. Cool. So you apply Snell's law. Thank you. I really like the way the students would tell me, like, or write down in your solutions that applying Snell's law, applying Newton's law, applying Ohm's laws, for example. I mean, the way we applied some tools in physics and then you deliver the results is perfect. Cool, thank you, good. So Tùng, here I also prepared, yes, the solutions, so I can discuss with you also, but the answer from Tùng is correct as well. And he delivered the values of the quantities, also the way how we can find them as well. So the angle of reflection here, which shows the direction of the reflected rays, is found from the reflection law, right? The law of reflection. So the angle of reflection is equal to the angle of incidence, is what we know so far from the law of reflection. So you got theta r equals theta a equals 60 degrees. Okay, correct. And then we applying Snell's law, and we can find the angle of refraction. Yes, you can find psi theta b. If you want to use another notation, I also repeat again, like, sorry, I also repeat that you can use another notation. Don't care about the notation here. Okay, you like another notation. Psi theta b equals NA divided by NB multiplied by psi theta A. Here. And the important things I want to mark with you also, in addition to the solution here, you should draw. We are in the world of optics. So always the drawing is important, okay? The drawing. So you got the value of theta b equals 49.3 or approximately 49 degrees. And the angle between the reflected rays and the refracted rays, here we go, this angle, right? So if you consider this kind of plane, you got 180 degrees. So you should do the subtraction, as to mention as well, of the angle of reflection, angle of refraction, and then finally you will got the value around 70.7 degrees. Good. So for the contribution of Minh Hoàng Tùng, for this example, you will, I note here, you will gain plus 1 point for the midterm test. Okay. Pay attention here, we got 1/10. You see, because the midterm test, you have 20 mark, but 20 points, but 10 for electricity and magnetism and 10 for the optics part. So if you have a chance to contribute during the course like Tùng just did, is also very, also useful for you guys, right? To gain 1/10 for the midterm test here. Yes. So thank you, Tùng. And maybe yeah. So Vũ Anh Tuấn, I think you need to apologize for the other classmates due to your, not a mistake, but just like somehow you make some noise during the class. So the other student also, please pay attention. We are in the online course, so maybe you can do some dual activities. However, don't make any things which disturb other students. Okay. So now we will move to another examples related to the index of refraction of some different materials. So here we consider the wavelength of the red light from a helium neon lasers, 633 nanometer. So here you see this value in air, that means red light. Yes, it is for sure. And this helium neon lasers is also used a lot in the experiment as well. In the optical experiment, we use this kind of wavelength lasers a lot. But the values of the wavelengths change to 474 nanometer in the aqueous humor inside your eyeball. So we will study our eyes in the next chapter, in which you will deal with the structure of the eyes, but in the physical point of view, not really in the biological point of view. We will see how the image is formed in our eyes as well, and we will see the different components of that. So here, inside that you got the aqueous humor. It is one part. And they asked us to calculate the index of refraction of the aqueous humor and the speed and the frequency of light in it. So like what we just did, I also leave you 1 minute. So for this example, so 1 minute. So anyone who want to discuss your solution? So yes, Nguyễn Nhật Anh, go ahead.
Yes, in this example, I will apply the formula for wavelength of light in a material, which is the lambda equal lambda 0 divided by n. And we apply the number as the example has given to us. I found that the number n is 1.335.
Yeah, so Nguyễn Nhật Anh just mentioned he used the relationship of the wavelengths and the refractive index of different materials given by this formula, right? So we got lambda equals to n lambda 0 divided by n. We just mentioned, so we can deduce that the refractive index is equal to lambda 0 divided by lambda, and it is equal to 1 point. So you have the correct number, like 1.335, right?
Yes. Yes, teacher.
Yes, okay. And for here, I do the round values. We got 1.33, sorry, 34, but it's okay as well. Yes. So the first question, the index of refraction. Okay. The index of refraction of the aqueous humor. Perfect. And how about the speed of light? Go ahead.
Yes. For the speed of light, I will apply the refractive index, which is n equal to c over v. And I found that it was the 225 multiplied by 10 to the power 6.
So
that's my answer.
Yeah, for the speed of light in that materials, we will abuse the formula V equals C divided by N. So the speed of light in the materials decrease N times, right? Compared with the velocity of light in vacuum. So you got 2.20 something. I don't remember your exact values here, but for me it's 2.25 multiplied by 10 to the power 8 meter per second. You got the values which is close to this, right?
Yeah, my value is still the same.
Okay, cool. Yes, thank you. And the last parameter.
Excuse me, can you repeat your question?
Yeah, I mean the last parameter, the last quantity, the frequency of light.
Yes. To find the frequency of the light, that I will find to the frequency equal to lambda divide. Let me check. It's lambda multiplied by v. Yes.
Lambda multiplied by V. Multiplied by V.
No, no, that I was wrong. I was wrong. I haven't done this.
You mean for the frequency of light you haven't done yet, right?
Yes. I wasn't sorry.
Yes. Okay. Maybe you haven't done the calculation for the frequency of light, but you can tell us like which formula or which relationship we need to use in order to find the frequency of light. For the calculation, like we put in the calculator is okay. However, the physical part is the relationship between different quantities. So which relationship you use here to relate the frequency and the velocity and also like the wavelengths, which relationship?
So we have found we have known the lambda.
Yes.
Lambda, and we also have known the velocity.
Mm-hmm.
And we can apply the formula that lambda equal V times F, the frequency of it. And we make a change a little bit of it, and we will have the final formula is for frequency that F equal lambda divided by V.
Yeah, so if you've got F equals lambda divided by V, so pay attention. Yes, I think you got some mistake here. And Đào Duy Mạnh Hà, I see also he sent me a private message in which he provide the value of index of refraction and also the frequency. And it makes sense for the values of Hà in the order, because normally if we have the nanometer for the wavelength, and then the values of the frequency should be in terms of the terahertz here, 10 to the power 14. So Hà, please, you can also discuss with us about how you find the frequency of this light.
Yes. So
yes,
when
continue.
when the light go from one environment to the other environment, so the frequency is the same.
Mm-hmm.
So in the exercise, the frequency from in the air and in the aqueous inside eyeball, it is the same.
Mm-hmm.
So I just calculate the frequency in the air.
Mm-hmm.
Is equal F equal V over lambda.
Yeah, and then you replace the values in air. Yes, thank you, Hà. And also thank you, Nhật Anh, for your discussion. Nhật Anh got some kind of like the mistake between the relationship of the frequency and the wavelength. For Nhật Anh, he put the wavelength in the numerator. So he put here wavelength divided by the velocity. So he put is like the inverse value. So pay attention. I will send here to, I will check inbox here, okay, everyone. So you can, that's why I discussed with you about the wavelength. Yes, so wavelength, as we just discussed, is the distance that the wave can travel in one cycle. So it should be wavelength, or we mentioned lambda equals V multiplied by T, or equals V divided by F. When you remember this definition, the distance that the wave travel in one cycle, so you got V times T and equals V divided by F, because T and F is inversely right in its inverse values. So it's reciprocal. F is 1 over T. Because I remind, the cycle is the amount of time that the particle finish one oscillation, and the frequency, how frequent it is. So that means it is the number of oscillation the particle can create in 1 second. So that's why you got D and F. We have this relationship. Oh, I'm so sorry, I made a mistake. D equals 1 over F here. So we got that. And when you remember the definition of the wavelength in this way, you can easily do the conversion, do the transformation between these different quantities, and then you can find this one. In terms of, in terms of the values, if we put here lambda in the numerator, and the velocity in the denominator, so you got lambda over v. So in that case, you will have like 10 to the power minus 17, for example. You will feel like it is very strange because small wavelengths here in terms of nanometer, that should go along with the quite large frequency. The wavelength and the frequency also has inversely proportional here, inversely proportional. So pay attention on that as well. Yes, so that's why we got F equals V divided by lambda. We replace all the values, and then we got 4.74 times 10 to the power 14 Hertz. So Hertz, the German scientist, and his name is used for the unit of frequency. In the world of electromagnetic wave also, Hertz contributes a lot. That's why they use his name for the frequency here. Okay, like Newton for the force, for example, is also to acknowledge their contribution in science. Pay attention on that. So very good. Nhật Anh and Đào Duy Mạnh Hà, each of you will gain 0.5. Okay, for the midterm test, I also note here in my notebook. So cool. And also I see the message from Vũ Anh Tuấn to all you guys. So pay attention. Not maybe today Tuấn made like the we say the mistake, but by accident, just like he didn't want to. I mean, he didn't intend to do that. But it also can be happen to us as well when we do the online meeting or like course. So please pay attention on that as well, and try your best to focus on the lecture. Even you will feel a little bit boring and tired during the online course, but and you can also spend some time to relax. But pay attention, you should focus on the course because only 4 classes, and then you will have like the test and so on. So if you follow the course carefully, you can understand the knowledge well, and then you can do the test well as well. Okay. So now we will move on the class to the next session of the total internal reflection here. So what we just studied is the 2 phenomena, reflection and refraction. And now here we will focus on the special phenomenon, which is total internal reflection. So when the light impinges to the surface of the 2 materials, always you will have the reflection for sure. But the refraction, sometimes yes, sometimes no. And when there is no refraction, we say that it is a total internal reflection, or I use the abbreviation here, TIR for short, the total internal reflection. So it is a phenomenon in which all of the light can be reflected back from the interface. So when the light meets the interface, there are 2 ways to go, right? The first way is to reflect back. The second way is to transmit in the other materials by the refraction. Sometimes it doesn't happen for the refraction. And if you just have the reflected rays only, you can exploit this ray. You can exploit that. You can use that to transmit the signal and so on. And then it is the application of the TIR. Okay, so here we go. We see in this figure 2 different materials with the refractive index NA and B. So when we study about the optics, you keep in mind also some concept like refractive index, or we say index of refraction. Yes, the name when we study the course in Vietnamese, you know the name for n, right? And you feel why is like this kind of name, but you study in English, you see it's obvious. Index of refraction n, because it will show how the rays of light will be refracted depending on the values of n, different direction for refraction. So that's why it got the name index of refraction n. Okay, here n, a, n, and b. And A and B here, we don't know yet. NA is larger than NB or NA is smaller than NB. However, if you look in the directions of the incident rays and the direction of the refracted rays, also we can conclude about the relationship between these two indices of refraction. So and in this figure, we also ignore some reflected rays. We don't draw that, only this for the last incident ray here. We draw the reflected rays. Okay, they occurs, but we ignore not to draw them. Sorry. So right now I will describe with you about these figures. So starting from the point source. So here you got the point source. We got the point source here, and we consider 4 different rays, 1, 2, 3, 4. So the first one propagate perpendicular to the surface. So it propagates perpendicular to the surface. That means the angle of incidence for the first case, for the first rays is equal to 0, right? Because we got here the normal here is perpendicular to the surface is here, and the angle between the normal and the reflected rays, for example, or the incident rays also equal to 0. They have the same line, and the reflected rays when go in this direction, also perpendicular to the surface. Yes, that's why always we will use this kind of ray in order to find the image. So as a spatial rays we use is this one. Easy, right? For the first case, equal to 0. I'm so sorry. I made the dot instead of 0. Okay, so in this for the first direction. Where I am, yes, here. And now we look at the second direction. For the second direction here, okay, for the second direction, oh, I'm so sorry, I check. Cô xin lỗi nhé, cô có một cô có một cái email của một bạn muốn join lớp mình, để cô sẽ trả lời bạn ấy luôn, rồi cô sẽ quay lại để học cùng chúng ta, vì là bạn ấy đã miss buổi sáng nay nên cô sẽ nhắn bạn ấy để bạn ấy join luôn bây giờ cho bạn đỡ bị lỡ học, vì bạn ấy ở khóa trước. Đợi một tí tiếp đi, sorry cả lớp, cô sẽ hơi gián đoạn một tí. Okay, cool. Lúc nãy cô vừa chuyển từ tiếng gõ từ tiếng Việt sang tiếng Anh cho tiện thì cô mới thấy email của bạn, nên là cô dành thời gian một vài phút để gửi thông tin lớp học cho bạn, thì bạn có thể follow cùng lớp được. Ok, Chu Bảo Minh, ok, let me see. Có một việc này cô lấy nốt Hoàng Anh. Các em mà có vấn đề về phần đôi khi có thể lúc các em cô anh Hoàng Anh hoặc là chị Hà mà điểm danh ấy, xong rồi các em chưa vào được, các em đi học muộn hay là các em bị gọi là ở các các em vào bằng điện thoại thì đôi khi đúng là ở trên điện thoại rất là khó để tìm tên mọi người trong phần chat ấy, thì nếu có vấn đề nhá thì cô gửi vào cái mục everyone này, đấy là email của anh Hoàng Anh đây, ngày hôm nay anh phụ trách ấy, thì em gửi email cho anh Hoàng Anh xong CC cô nhá, thì để cô sẽ follow cùng, còn việc attendance thì là anh Hoàng Anh sẽ xử lý đó. Không thì cô có thể bị miss thông tin, vì các thầy cô đôi khi cũng bận quá lại bị quên mất các thông tin các em trao đổi. Ok rồi, bây giờ chúng ta sẽ lại quay lại bài chúng ta. Cô xin lỗi vì đã làm gián đoạn của các em một chút. Chuyển từ Anh rồi. Okay, so for the second phrase here, the second one, so the second direction of the incident ray, so you see another incident angle, so this ray meet the surface here, so we draw the normal perpendicular to the surface at the incident point, and theta A here is the angle of incidence created by the normal to the incident ray. Okay, right. So now we will find the refracted ray here. They also draw for us already. So we see theta B is larger than theta A, and the refracted rays goes further, right? Go further from the normal. So for that, when we use Snell's law, we see even we don't know the relationship between NA and NB, the indexes of two materials, but we know so far that theta B larger than theta A means that NB should be smaller than NA, is what we can conclude with the understanding of the physics, right? So you know theta, the NB here. With this direction, we got theta. They draw already theta B is larger than theta A. So remember, theta B is the angle of refraction, and theta A is the angle of incidence. So we can deduce that NB is smaller than NA from Snell's law. Okay, so if we keep increasing the angle of incidence here from 0 to theta A and then to another angle here, we note with the name theta crit, or we say the critical angle of incidence. So for the third direction, theta crit, or we say the critical angle of incidence. So we increase the angle of incidence from 0 to theta A to the theta crit here. In this case, we got that. And if we observe the refracted rays, we see that it goes in the same line with the surface here, the same line with the surface, right? And the angle of refraction for the case of the third direction already equal to 90 degrees, right? 90 degrees. So no, it is impossible to the angle of incidence or angle of refraction or even angle of reflection to be larger than 90 degrees, because it is formed from the normal to that ray. So this is the maximum angle of the angles of refraction. If we continue increasing the angle of incidence larger than this angle, critical one, and then we don't observe the reflected ray anymore, we only observe the reflected rays. So it is the so-called total internal reflection, TIR. So here we got the reflected, here we got the reflected, here we got the reflected as well. but here no, we got the reflected, but no refracted one. So it is a so-called TIR, total internal reflection. And we can find easy the angle critical using Snell's law. So using Snell's law, we have that sine theta b, that means 90 degree, right? So we put NB multiplied by sine 90 degree equal to NA multiplied by sine of theta critical. Here, right? So you can deduce sine theta critical equal NB divided by NA. That's right. So here, this material is water and this material is air. So you see, we observe the phenomenon and even we can at first don't care about the material. We just care about the direction of the light. We can conclude NB, the index of refraction of the material B, is smaller than the index of refraction of material A. And yes, here in our case, Na is equal to 1.33, for example, is water, and here NB is equal to around 1 for air. And we got the first condition for the TIR occur is that NB must be smaller than Na. So light travels from larger refractive index to the lower one, or we say like the denser to the less dense optical materials here. In order to achieve the TIR, as I show you here, is the phenomenon we observe in both. In fact, both we have the refracted rays, and also for the case we don't observe the refracted rays. So in that case, we see the first condition is about the refractive index between these two materials. Imagine if NB is larger than Na. So here you will have this angle should be smaller than theta A, here smaller. So that means always you will observe the refracted rays, always, yes. So that's why the first condition is that NB is smaller than Na. Light mass travels from the higher refractive index or larger refractive index to the lower one. It is the first condition. Yes, so for the condition is that Na larger than NB. And the second condition is related to the angle of incidence. If the light penetrates a very small angle of incidence, so for sure we can observe refracted rays at some other angle of incidence which is larger, and then no more refracted rays anymore. So the incident angle theta A is larger than or equal to the critical angle for total internal reflection, or we say theta critical. So that is why it got the name critical angle. Yes, so the critical is like the boundary or the limitation values, so that this phenomenon happens or not. So we got here, in this case, the incident angle is larger than or equal to the critical angle for TIR. Okay, so you got that. And the values of the angle, the critical angle of incidence is calculated by this formula. We got sine theta critical equals NB divided by Na, and I just also prove with you in the chat box as well. So we will see one example in which we can do the very simple experiment in order to observe the total internal reflection. So you can use a red laser light beam, and then you inject into the vase, the vessel, in which here is air and here is water. Okay, and below the water you put two different mirrors at two different angles. We can change the two mirrors at different angles here. So and then we inject some different incident laser beams here. So for the case here, if we look at this incident ray, we inject perpendicular to the surface. So it goes like this one, and then it will be reflected at this interface of the mirror. And then at the interface between the water and the air, you observe the reflected ray. It is one, one ray. Another one, if we inject this incident rays here to this second mirror, and then it meets the mirror at this point. So you observe the reflection here. So reflected ray at this surface of the mirror, and then at the interface between water and the air, because the angle of incidence is large enough, so we don't observe the reflected rays for the second case, only the reflected one here. And then at this boundary, we observe the output signal like this one here. And here you got the reflection here as well, you see here. So here is a part for the reflected rays at this surface to go out through this interface. But and here, this part, you can observe the reflected rays. Okay, so here's one example related to the TIR, very easy experiment. And now the important things for the TIR is that, why do we need that, right? We say, okay, we use TIR in applications as well. So we will discuss on the application using the TIR. So let me remember what I discussed with you from the beginning of the class and move to the chat box a little bit. So I just mentioned with you about laser. Okay, cool. I haven't mentioned with you guys about also one important invention which used a lot in ICT. Yes, for guys who work in ICT, and even for us now when we do the class online like this one, we need the development of the so-called optical fiber. Yes, and in fact, optical fibers are created using the TIR. We will discuss this in the application part right now. So first, we will discuss on the porous prims first, which use the TIR. So the porous prims here, this is the prims. So we got the prims. Prims normally will have this shape, the triangle, and this one is the right triangle. And in this case, we got the right triangle for prims. In this case, for the porous prims, we got the right triangle, and which is made of glass, right? So it made of glass and surrounding is air. And here the nice thing is that we got the right triangle. So, and we got the equilateral right triangle. So here is 45 degrees and here is 45 degrees as well. And the hypotenuse side here with this angle is 90 degrees. If you inject the light perpendicular to the hypotenuse side, hypotenuse one, here you inject here. So it will first go straight, and then it will meet this side, right? And then it will reflect it like this one. And we wonder if the reflected rays appear or not. So in order to answer this question, I would say that like, no reflected rays. And why? Yes, okay, we have also the answer right here. The prims is made of glass, and the refractive index of the glass we consider here is like 1.52 or 1.55 surrounding that value for the glass. And the prim is made of glass, surrounding is air, so we can find the critical angle for the total internal reflection is equal to the refractive index of air divided by refractive index of glass, right? So you've got 1 divided by 1.52. So we got the value of 0.658. And the critical angle is around 41 degrees. So if we got here, the angle of incident is equal to 45 degrees. So it is larger than the critical angle between the glass and air surface. Here, higher refractive index material and then lower refractive index material. So the first condition for TIR is satisfies. And for the second condition related to the angle, also we have here angle of incidence larger than the critical angle of incidence. So we have only total internal reflection. So the light reflected like this one. And at this surface, similar also, if you draw the normal, it should be 45. Yes. So it is also larger than the critical angle. So it also reflects again, no reflected rays at this side. So it's how we can control the propagation of the light with this kind of optical device. So here's the so-called probe prims. And this binocular use 2 probe prims, one here. So they will arrange them in the right order, so that if you want to observe something, you will yes, the signal or the incident ray coming this way, and then it will be reflected here. Okay, here, go again in this way, and then the output here. You can. So we see that the binoculars use probe prims to reflect the light to each eyepiece, and then you can observe the object. So it is how the TIR is exploited in order to observe the object. Yes, it can be used for the enemy, for example. Second popular applications is what we use in the hospital in order to check your internal organ. We can use some tools using the optical devices, like you can use X-ray to capture your body and then to check out, okay, your lung has some problem, like here in the COVID-19 pandemic. Unluckily, you can get the virus, and it will also be harmful to your lung. And then you come to the hospital and check, and then you can see how the lungs is changed also. So you can use X-ray. Yes, you can check that with a photo. And maybe you can use another tool if you want to test your stomach. Yes, the stomach, you got some problem, and also the doctor want to do some operation with your internal organ, and they can abuse the endoscope. So it will go through the throat and then also some other position in your body, and then they can observe what happens inside your body as well. So it is the endoscope using the TIR phenomenon. And now the last one I mentioned in the application part related to the fiber optics world, and it also has a tight relationship with you guys who study mainly on ICT or cybersecurity here. Yes, in this L2 class, we got ICT, CS, DS, and math as well, right? So in this era of the communication, we have the development of the communication as well. In order to implement this online course or online meeting and so on, you need some devices to transfer the information. So from the 1960s, it is the period in which lasers, optical fibers also was developed a lot here. So we have here this figure. The quality is not so beautiful, and I'm so sorry for that. But you see the structure of an optical fiber. You see the core here, the cladding, and here the plastic coating. So here is one material, and the cladding part is also another material. So do you guys who know so far about the optical fiber, do you know the materials which can be used for making the optical fiber? If not, I would like to tell you directly, it is silica. Yes, silica or the silicon base, which is also very popular in our world as well. So, and also it's cheap. Yes, what is cheap, what is popular, what is abundant should be abused in order to make the materials, in order to create the new devices. And silicon normally will be used a lot in electronics, like in your computer, and the ICT guys like you also need that a lot. Here, if we send the signal like this one, and the light rays coming here to this core part, and the core has higher refractive index than the cladding, and so at some incident angle, it will be only reflected, not refracted one. So we have here the TIR as well, right, inside that. So the information can be transmitted. So the optical fiber, with the development of that, we can do the information communication like this one. So we have the so-called fiber to the home. Yes. So the fiber to the home, FTTH here. Well, and in the street, you will see a lot of optical fiber, right, as well. And then when the technician, they connect, like you use Viettel or FPT or VNPT, they connect the internet to your home. Inside your home, you will use another connection, not the optical fiber. Inside the home, you will use the LANY, which is made of copper. Yes, so pay attention. For the optical fibers, you use the light to transmit the information. And for the copper, you will use electron to deliver the signal, right? So electron for copper. So copper, if you cut the wire of the inside your the internet inside your home, you will see which is a copper. Okay, and for the optical fiber, you will use the light. It is a concept. So, or you say like you can use photon. Yeah, okay. So here, with this kind of development, we can do the, for example, the online class like this, very convenient. Without optical fiber, no, for sure we can do that. Yes. So here I show you the size, because you will wonder what is the size of the optical fiber as well. So here is a cross section of the optical fiber. In the central part, which is the core here, and you got the cladding part, and then finally you got the coating. The plastic coating here is to protect the core and the cladding part of the optical fiber. And the size of the core, yes, you see here 9 per 125 micrometer. So you see, in terms of micrometer, not centimeter or millimeter, it is micrometer. So in fact, it is very, very small. So you can use like a lot of optical fiber in order to transmit the information. So it is very convenient. And the nice thing of using this as well is that you have the plastic coating, so it will prevent the light it will prevent the light from interfering with each other. So the signal has like no noise, for example, no loss, for example. So you see it's a very high advantage of using the optical fibers. And the size here, you see, is very small. So for these, for you guys who are in this class, you are mainly ICT, CS, Math, and I forget the last one. Sorry, ICT, CS, DS, and Math. So you may only focus on the communication, for example, but the students or the people who work in the field of the advanced materials science and nanotechnology, for example, they will help you to find the proper materials for this kind of core and cladding. They are both silica. However, one is pure silica and the another one is the impurity silica as well, to have the different refractive index. So you see the refractive index of the clad here, the cladding, and the refractive index of the core is only slightly different. So here the values is 99.9% of the core. So the core higher refractive index, normally it is the impurity silica, and the cladding is a pure silica. So in order to make this kind of optical fiber, also we need some help from the guys working in advanced materials here. So you see the relationship between different measures, different specialty as well. And in 2009, Chanska also got the Nobel Prize in Physics for the contribution in this domain of the optical fiber as well, for the investigation that. Showing you here this, maybe the last figure related to this topic, we see here is an optical fiber a lot, right? And you see very bright at the end, shows that these optical fibers can transfer the signals to the end. Yes, this is how we can obtain here, very bright and very beautiful one. You see, so it's how I also received some questions from students that, okay, why do we need to study this kind of subjects like physics or biology if I am an ICT guy, or if I am a student who works in PMAP, why we need the physics, for example. However, what you study in the first year are the general physics, because it's fun. Okay, cool, I agree with you. Fundamental physics, general chemistry, and also like and linear algebra, calculus 1. Even maybe you don't study like the other courses related to physics anymore. However, it helps us to understand what is happening surrounding us related to the nature, and also how we can abuse this kind of things, this kind of phenomena, in order to apply it in our daily life. Yes, so in order to understand the world, it is what I mean. So also the optical fiber and the laser and so on, the inventions in the 1960 with the lasers and the optical fibers, which help the people on our Earth to communicate with each other. So that's how you can have like Facebook, and you can have like other internet marketing, or like you can have the business all over the world, the virtual one, right? And during the COVID-19 pandemic, without this kind of development, how can we continue our life? You see, so that's why for the first year, spend some time to study the basic knowledge in order to understand the world, and so that we see that the world becomes flat. Yeah, very nice question from Nguyễn Minh Hoàng. Like, why do you like to use the word abuse, teacher? Yes, it's like has a different. I mean, like the spirit, the aspect of this kind of word. Maybe you can feel like it's a bad word also. However, in science, the word abuse is not so bad like the daily life, and it's also like the in my habit only when I use in the scientific domain. I'm so sorry, it can make you a little bit like wonder why I use that so much. However, like employed or exploit or abuse or applied will be used quite often. Okay, so very good that you followed the lecture very carefully, and then you also asked me some questions. I really enjoyed that kind of things. Cool. So let me think if I forget something related to this part, the total internal reflection concerning the optical fibers. Yes, I think no. So good. Is this okay for you up to now for the course? Okay, no response, so I think yeah, it's fine. Okay, here we go. We will have one small example as well related to the part of the total internal reflection. We got a Lippy periscope. We got here in this exercise is a submarine periscope, uses two totally reflecting 45, 45, 90 prims with total internal reflection on the sides adjacent to the 45-degree angles. Explain why the periscope will no longer work if it springs a leak and the bottom prims is covered with water. So basically, when you see this kind of question, you should figure out some clues here. So the first thing is that for the prims we use, it should be the interface between the glass and air. So it is the first point. And now if it is leak, so that means the air will be replaced by the water. So different interface, different couples of the materials. And then here we got the 45-degree of the angle of incidence, and then it will change the angle, the critical angle of incidence when we consider different couples of the materials here. So for this kind of example, I will discuss with you immediately for fast, because we don't have like so much time, but I will do the hint and then you will do the rest of your at home as well. So here the couple of the environment will be different. So it will be water and glass. So we calculate this value and then we compare what the critical one is here, but the angle of incidence is 45-degree. So it is not sufficient, right? With the critical angle, it is not larger than, even smaller than lot. So that's why we don't have the TIR anymore. So it is a so-called the leaky periscope, and it will destroy the scope now. And pay attention, you have the scope. So the meaning of the word scope in physics, it is to observe, it is to characterize as well. So it is the meaning of scope. Okay, now we will move to the next content of this chapter. We will deal with the so-called dispersion. Dispersion, so dispersion, also it related to the prims. It will also make you think about the prims as well. So the dispersion here, what is dispersion? So the dispersion is a dependence of wave speed and index of refraction on wavelength. Yes, so the velocity and the index of refraction and on the wavelength. So showing you here is a figure which shows the relationship of the index of refraction and the wavelength. And here we use the wavelength in Bacon here, lambda 0, that's value from 400 to 700. And also is also a nice illustration in which they also draw the color corresponding to the wavelengths in Bacon here. Violet around 400, blue, yes, green around 500, yellow around 550, and then orange around 60 something, and then 65 from now on we have the red color. So you see very nice illustration for that. And when you obtain some experimental results, or even you do the theoretical research, if you want to plot the function over the variables, so we say here fx, for example, you will need to use this kind of figure. So the horizontal axis shows the variable, and here is the wavelength. And the vertical one will show the function, which is, in this case, is the index of refraction. Okay, so function, variable, it is clear, right? And different solid, so the black solid curves here are the index of refraction versus the wavelength for different materials. So we got fluoride, fused quartz, silicate, crown glass, quartz, boratus flint glass, and silicate flint glass. Okay, so we have different substances here. And this curve is different from this curve. Everything is different, yes. So it is typical for each materials, the refractive index. will depend on the wavelength. So how it depends here? Like when you send a white light to the kind of glass, for example, of the prime is made from glass, and after some refraction, we observe in the outgoing signals, it's not the white light anymore, but now you will have different different colors, right, in different direction, or we have the so-called deviation as well. So it comes from that kind of dispersion. So if we consider the fluoride, so at different values of the wavelengths, we see that the index of refraction also change, but not that much, right? Because the slope here, you see, more or less it's like flat. But if we come to another one, like the silicate ground glass, for example, we see here at 400, the value is 1.52 something. Yes, 1.55, and here it should be like 1.52 something at around 400. However, if we move to 700, and then it's just like 1.5, right? Close to 1.5. And the slope here, you see, is more thin compared with the fluoride. And now if we consider the silicate flint glass, first we see the values of the index of refraction of this material is higher than the fluoride, for example. Different materials, different value of index of refraction, yes, for sure. And for the slope of this curve, you see, is also got quite large slope, right? At 400, the values of index of refraction, more or less around 1.65, so 1652, for example. And for at 700, it should be like 161. Yeah, so you see the difference between the values of refractive index for two ash wavelengths is very different for the silicate flint glass. I'm so sorry. Okay, so here we see the relationship, the wavelengths also in different materials is different. We got lambda equals to lambda 0 divided by n. And for the dispersion, we got the properties that for most materials, we have the fact that the index of refraction increase or decrease. Okay, I will say following my notation here, decrease or increase with the increase or decrease of the wavelength. So here, higher, longer wavelengths, lower refractive index, right? You see, yes, it decreases over the wavelengths. And wavelengths and frequency, please keep in mind, they are inversely proportional. So the relationship of some quantities in physics, we use inversely proportional or proportional is what we normally use. So I also mentioned here with you guys again, maybe some of you forget, I just mentioned. So we got that. And if we move to the longer wavelengths, I also want to mention you one term in optics, wavelengths. We got the term redshift, okay? And move to the shorter wavelength. We sometimes mention blue shift. Oops, I'm so sorry. I made a mistake in typing blue shift. Here we go. And the amount of dispersion depends on the difference between the refractive indexes for violet, this ash, and for red light here. So that, like here, the difference is large. So you have high dispersion. Here you got the difference is quite small. So you got low dispersion, right? Yes. Very beautiful one. When you send a white light to the prims, so here's the direction of the incident ray, and here they use a dash. And normally when you draw the rays of light, you also use a dash when it is, I mean, unreal, right? It is like only the imaginary line here, this part, because the rays of light will penetrate like this. Even the rays of light, also the imaginary line. However, when we draw this one, we consider that is real. Okay, so that's why you use a solid one. And here, the light will not penetrate in this direction. So if we want to see the initial direction, we will use a dashed line here. And then inside the print, the light will be split in this way. And when at this adjacent side, we got the white line now become different monochromatic wave color. Okay, so mono, that means one, and chromatic about the color. Yes, so you see here from the red in this direction and the violet in this direction. So for example, if we consider the yellow light here, so the change of direction of this light ray with the initial incident light right here is the so-called deviation of the yellow light. And here will be the deviation of the red light. And if we measure here the green one, for example, we have the deviation of the green light. And this angle is a measure of dispersion. So from the violet and the red one. Yes, you see here. Okay. So higher refractive index for the violet. So that's why it refracted a lot here. And lower one for the red color. So it reflected not that much here, the angle. We got this red here, red, orange, yellow, green, blue. Also, you will have some other mixture of color, but I also mentioned some basic color here. So you got the violet one as well. And then finally, you got the measure of dispersion here. So it is the so-called the dispersion of the light. And the dispersion of the light helps us in some beautiful phenomena. Like the first slide I present with you for the name of the Cox optics. I also show you the picture of the rainbow. So we will explain about that. And we have the term of the spectrum. So which is the band of the color of the light by the prim. So we got the spectrum, which is the singular now, singular. And if we move to the plural, it should become to the spectra, the plural here. And normally you can observe the spectra, you can obtain the spectra during the optical measurements. So it is what we will use a lot for guys who focus on the optics domain. So now we will use the dispersion to discuss some natural phenomena. Here is a rainbow. So this one, beautiful one, is a primary rainbow. And you also see some blur rainbow behind that as well, right? We got it, the secondary rainbow. So depending on the way the light interact with the raindrop or the water drop, and then you can observe the rainbow, the primary one or the secondary one. So it depends on the direction, on the position you obtain, you observe, and then you can see this kind of rainbows. So if you need the rain, okay, no rain, no rainbow, that's why. So showing you here's a figure to illustrate how the light rays from the sun will propagate when it meets the raindrop. So the raindrop here. And imagine you are standing here observing that, and the sun is behind you. Okay, so the direction of the incident rays like this one. And we draw here in the half part, the upper one only. If you draw also for the lower, it would be like also the same what happening here, but we will do the symmetric properties to draw that line of the refracted one, or do we say the outgoing the light. And this we will draw here from the first to the sixth. So the first one goes through the center of this raindrop here, and we see here the down sun point here. Okay, this point we will discuss later on about that. So it's the first incident ray, the second one, the third one, the fourth one, until we can draw here 6, or you can draw even like 100 or 1000 as you want. But the two boundaries is that the first one passing through the diameter here with the center of the raindrop here, and the last one will pass by the edge. Here you see the edge of the raindrop, and in the middle we will have different other incident rays. So we will have a look how the light rays from the sun wind goes when it faces the raindrop. Here we go. It has the direction, the first one has a direction like the diameter. So it will go straight, right? Because the angle of incidence is 0. For the second one, you can draw like this one. In order to make it more precisely, for the drawing, if you want to draw more precisely, you will make the tangent line here, and then you draw the normal, which is perpendicular to this tangent. And in fact, it is the radial line passing through this point and the center of the sphere of the raindrop. Yes, so you got the normal. Okay, and then here you got the angle of incidence and the angle of refraction, and for sure the angle of refraction must be smaller than the angle of incidence, because you have here water, you got here air. Okay, so higher refractive index, that means the angle of refraction should be smaller than the angle of incidence. So it's what we will use to draw. So here for the edge point, okay, so you have this, for example, this one, and you can figure out the refracted rays here. So they will penetrate, the refracted rays here penetrate inside the raindrop, and then they will meet other interface. And then at this part, you will have the reflection here. So the reflected rays when goes in this way, and then until it faces another boundary, and then another interface, and then we have the refraction. Okay, so this point is the incident. Okay, and then the final one, the largest one we consider here, which deviate a lot here. So the largest deviation here, and then you can see the intersection of these two rays. It will create here the down sun point, and we got delta here is the maximum angle of the light from the raindrop here. And pay attention here, we draw only for the half upper part, and if we use the lower half, you can draw as well, right? But then you will make the using the symmetric property, you can also be able to draw the outgoing rays. So for this case, we got the light from the sun. We make for the east, we will use only one line like this one. And then it will reflected inside the raindrop and reflected as well here at this boundary, at this interface, and then reflected as well. So we got here the red color, and here the violet color, and you can make it the extension mark, and we can gather here at this point, okay, at this meeting point. So we got the angle for violet here, theta for violet is around 40.8 degree for violet one, and for the red one is 42.5 degree. Yes, the red is here, the violet is here. So we got the violet is inside and the red is outside color here. And we get, that is the case of the primary rainbows. So the primary rainbows is formed by rays that undergo 2 refractions and 1 TIR. Okay, so I made a mistake here. It should be TIR. This morning I also realized that, but I forgot to correct that. So sorry. So it's not ITR, it's TIR, total internal reflection, this part here. Okay. And now in the second case, in another case, yes, we got lambda red rather than lambda violet one. So that's why the red is outside here. And for the second case, if the light from the sun go in this way, and then it will experience first reflection, second reflection, first reflection, second reflection, right? So for here, because due to the refraction, also we got the dispersion, it makes the color to be splitted like this one. Yes, here you got also. So we will achieve the light from the sun here. So the angle for the red in this case is 50.1 degree, which is smaller than the violet one. So that's why for the secondary rainbows, we observe here the red and then the violet outer part. So a secondary rainbow is formed by rays that undergo 2 refraction and 2 total internal reflection as well. Yes. So that's how you can abuse the refraction, the reflection, and the dispersion in order to explain the optical phenomenon around us, like the rainbows here. Good. Yes, in this case, the lambda violet is larger than the lambda red. Okay, now we will move to the part of the so-called polarization. And pay attention, as I mentioned from the beginning of the lecture today, we know also this term, but in electricity and magnetism for another phenomenon. Here we have the concept of polarization in optics. Pay attention, polarization in optics. So we will, in order to have this polarization definition, we must consider light as a wave. And you all know that light is an electromagnetic wave. Yes. We all know that. And an electromagnetic wave has 2 components, or we can say like 3 components. That's fine as well. So they are the electric field, the magnetic field, and the velocity of propagation. Right, we got this type of things. And for the electromagnetic wave, for the light, the electric field and the magnetic field and the velocity of propagation, they are mutually perpendicular. Okay, so I think you already had the final test for the fundamental physics 1 for the mechanics. So you guys, when you study the FunPhy 1, we say for short FunPhy 1, about the wave, the mechanic wave, in which you will classify the wave into different types. So you have the transverse and the longitudinal wave. Yes, you agree, right? The transverse and the longitudinal waves. So depending on the direction between the oscillation of the particle and the direction of the propagation of the wave, and then you can decide the wave is transverse or longitudinal. So it depends on the direction of the oscillation. I write down here to remind you, yes, about what you learned so far, for those who may forget. And then you can decide transverse or longitudinal waves. If they are perpendicular to each other, we have the transverse, like the water wave, for example. If you drop the stone into the lake, for example, you will observe the water wave will be expanded, right? So the direction of the propagation of the wave will be along the surface of the water lake as well. And if you put some a marker to the surface of the water and you observe, like the marker will be go up, go down, go up, go down, right? It's oscillate surrounding the equilibrium point and then perpendicular to the direction of the propagation of the wave. So for that case, we call that transverse wave. And if we look at the sound wave, yes, if you like the sound, for the sound, the oscillation of the particle is along the particle. We can say like the particle along the direction of the propagation. So it is longitudinal. Yes, so that part you remember well, right? Okay, so I do the review a little bit on that because now we will define the polarization of the light. If we look at that, and the polarization of the light, how can we define that? How we can say the light is which type polarization? So we got the transverse wave here. In this case, for transverse wave here. So this arrow shows the propagation direction of the wave. So it will transmit in this direction. Okay, so along X direction. However, we got the red or the purple. Okay, the purple, I think the color is purple. The purple colors shows the oscillation direction here. So if we look like this, it means that it oscillates along the y-axis, right? Yes, along y-axis. And here, you see, and here in this case, if we consider this example, also propagates, the wave propagates along X direction, and the oscillation is along the Z direction, you see here, in the XZ plane, we consider, yes, in Z. And here along Y, if we look at the X or Y plane, so the Cartesian coordinate. Here, so in this case, we will call this transverse wave linearly polarized in the Y direction. Here, the oscillation. Yes, we got the transverse because the direction of the oscillation, Y, is perpendicular to the direction of the propagation here of the wave. So X, so that's why we got the transverse. And if this oscillation is only along one direction, it is only along the Y direction here, we say that it is linearly polarized. Yes, later on you will have the concept of circular or the elliptical polarized as well. We will discuss about this later on. And here in this case, the transverse wave linearly polarized as well, but in the Z direction. Yeah, you see along Z direction. Clear, right? and here, if you have this oscillation like this one and passing through some barrier along the X axis here, and if you put the slot here, so the slot which is parallel to the Y axis, so only the oscillation along the Y axis can pass through this barrier. So this acts as the polarizing filter, because after passing this barrier, only the Y polarized will be transmitted only. So the slot plays as a polarizing filter, passing only components polarized in the Y direction, because this here is put parallel to Y. If you put parallel to Z, you will have like only the Z linearly direction. And if we consider for the electromagnetic wave, as I just mentioned with you, for the electromagnetic wave, I will talk about this later on, the final one. If you see these two components, electric field and magnetic field, for the electromagnetic wave, the two main fields are electric field and magnetic field. And I denote them in bold like this one, that means the vector, okay, the vector one. So if you see in the formula, you got cosine of kx minus omega t. That means the wave propagates along x direction. Yes, you got kx. That's why kx minus omega t. So any wave, the function will be of the space and the time. So you got here, and E is a function of x and t, and equals to vector j multiplied by E max, the amplitude, times the cosine kx minus omega t. So we got here b, also you got b as a function of x and t equals vector k multiplied by b max cosine kx minus omega t. So you have the term of I, j, k. So you know I, j, k, they are the unit vector of Cartesian coordinate. So corresponding to OX, OY, and OZ. Yes, so it will show the direction I along X, J along Y, and Z along, K along Z. However, the values of I, J, K, the magnitude is equal to 1. So when you have this type of unit vector, it has the magnitude equal to 1. The magnitude of I only remind you because I know that you already remember very well for that. So the magnitude equal to 1 is a unit vector, and it shows the direction of OX, OY, and OZ. So if you look E, the electric field in this manner, so that means E oscillate along the y-axis, and B oscillate along z-axis. Yes, because the direction here J and K, and it will propagate along x-axis, propagate along x, but the oscillation of E is along y direction and B is along z direction. And the polarization of the light is defined by the direction of the electric field. Here, pay attention, the direction of the electric field. So if you have the electromagnetic wave presented by these two expressions for vector E and vector B, we will conclude that the polarization of this electromagnetic wave is linearly in y direction. Okay, so it is linearly polarized in the y direction. Yes, pay attention, because here you see the direction of the oscillation is along J, and X here is the direction of the propagation of the wave. So it is the main message I want to tell you for the concept of polarization of the light. It is defined by the direction of the electric field, of the vector electric field. Okay, why we don't use the magnetic field to identify the polarization? Because many optical materials, also you can have a look to the answer of this question, but I also tell you immediately, because many optical materials, they don't possess the magnetic properties at all. So we don't care that much about the polarization of the light by considering the magnetic field. It will be decided by the direction of the electric field. Keep in mind that. So here we have one example of the antenna here, the broadcast antenna, in order to provide the signals, right? I know that a little bit now, I mean over time, but please keep calm and we will continue to finish this part. So here we have two parts with two different colors, the white and the red one, so which made of metal, right? So here the electrons will oscillate vertically, and when it oscillates vertically, it will produce the vertically polarized electromagnetic waves, and that propagate away from the antenna in the horizontal direction here, because the direction of the propagation of the wave and the direction of the oscillation must be perpendicular to each other. Here we got that for the electromagnetic wave. And if we look at this lamp, the filament here, it will produce the light wave in all direction for the electric field oscillation. So we got the so-called unpolarized light waves here. And here you can observe in the visible range. So that's is a key point in this part when we consider the polarization of the light. It is the direction of the electric field. So please keep in mind that. Maybe you guys will never study with me about in the next course and other course in the electromagnetism or the optics part. However, after finishing the course of optics, I do hope that you keep in mind polarization of the light is defined by the direction of the electric field. So, and also maybe somehow further on you will deal with some kind of concept like this one, and you have this in your mind as well. Okay, I really want to finish this part, and I don't know if you agree or not. To leave me like 4 minutes, 4 minutes. Okay. No response. So okay. So we will deal with the polarizing filters. The filters to select, to filter, yes, the polarization and how it can work. So firstly, we want to say that the polarization filters depend on the wavelengths, and then you can have different configuration or different structure for that depending on the wavelengths. For example, showing you here is another example, but firstly, if we deal with this wavelength range, the microwaves, that means like few centimeter wavelength. So not in the optical range, right? The optical one should be in the visible one we normally consider. So it should be very short, but microwaves, it should be, the wavelength should be quite long here. And in that case, a good polarizer is an array of closed space and parallel conducting wires that are insulated from each other, and then that's how we can filter in this kind of direction. And if you move to another wavelength range in the visible one, so we use a Polaroid filter here. So normally it is used for sunglasses or the polarizing filters for camera lens, for example. So in this case, when we deal with the visible light, the structure will be different. We will use this polarizing axis here inside this Polaroid filter, and the polarizing axis is vertical, right? So that's why if you have an unpolarized light like this one, so here it is the orientation of the electric field oscillation, so in different or in random directions. So it is so-called unpolarized. So passing through this filter, you see here, only the one which is parallel to the polarizing axis can pass, and the other one which is perpendicular should be absorbed. So here it can pass less than 80% the intensity of the wave that is polarized to the polarizing axis, and the other one, especially for the one which is perpendicular to this polarizing axis, will be absorbed. So only like smaller than 1% can pass if it is perpendicular to this axis one. So it is some examples, and okay, I want to move to the using polarizing filters, but we can do that in next time. I don't want to force you that much. So we can stop the class today here. Also, I really want to finish this. Okay, never mind. We will continue next Friday, and I would like to aware you as well. Like for the next class, the speed should be a little bit fast. I mean, because we have a lot of content. But compared with the electricity and magnetism, I think it is can be comparable, because for the previous part is a lot. So would you like to stop the class now? Okay, we will stop the class now. I mean, okay. I want to. Yes, I see. Okay, so thì chúng ta sẽ tạm dừng cái buổi học ngày hôm nay kết thúc ở đây, và nếu các em có vấn đề là cảm thấy học có vấn đề gì đó thì các em có thể feedback lại với cô nhé. Email của cô thì cô sẽ gửi lecture note cho tụi em trong hôm nay, và các em cũng sẽ nhìn email của cô, để có vấn đề gì các em có thể trao đổi với cô. Thế nhá. Rồi, hẹn các em vào thứ 6 tuần sau. Các em có ổn không?
Chào cô.
Đúng rồi, các em còn có lớp học nữa và tiếp theo, đúng rồi. Ok, bye cả lớp nhá. Cô cũng đi họp đây. Bye bye các em.
Chào cô.